Dear students, in this class we are going to discuss about the chapter P block elements. Based on the entering of differentiative electron into the subcell, the elements are classified into 4 blocks. So based on the entering of differentiative electron into the subcell, the periodic table elements are classified into 4 blocks. They are S block elements, P block elements, and D block elements, finally F block elements. So that means there are 4 blocks in the periodic table based on the entering of differentiated electron into the subcell. Now, what are P block elements? P block elements. In these elements, the differentiative electron enters into the P subcell of the outer orbit. For example, if the differentiative electron is entered into the P subcell of outer orbit of any element, that element belongs to P block. For example, I am taking one of the example, that is boron. Now I am writing the electronic configuration 1s2, 2s2 and 2p1. So this is the lost electron or the differentiative electron as compared to the previous element. So this electron is entered into the P subcell of outer orbit. That's why this element belongs to P block. Right. So P block elements generally in the periodic table exactly present at the right side. And there are 6 groups present in the P block. So those 6 groups are 3rd A, 4th A, 5th A group elements, 6th A group elements, 7th A group elements, and finally 8th A or 0 group elements. P block elements. There are 6 groups are present in P block. They are 3rd A, called also boron family. Outer electronic configuration is Ns2np1. Boron, aluminium, gallium, indium and thallium. These are present in 3rd A. And next group is 4th A, called also carbon family. Outer electronic configuration of these elements Ns2np2. Elements carbon, silicon, germanium, tin, stannum, plumbum or lead. These are belongs to 4th A. And 5th A, nitrogen family. Outer electronic configuration is Ns2np3. Elements nitrogen, phosphorus, arsenic, strontium and bismuth. 6th A group elements. These elements generally calling as a chalcogens. Outer electronic configuration is Ns2np4. Elements oxygen, sulfur, selenium, tellurium and polonium. And 7th A group elements, these are called also halogens. Outer electronic configuration is Ns2np5. Elements fluorine, chlorine, bromine, iodine and astatine. And last group in the P block, that is 8th A or 0 group elements. These elements generally we are calling as inert gases. Elements helium, it has a specific configuration 1s2, and remaining elements are neon, argon, krypton, xenon and radon. So from these outer electronic configurations, straightly we can write Ns2, Np, 1 to 6. This is the outer electronic configuration of P block elements. This is the general outer electronic configuration of P block elements. So in the first year syllabus, you are already learned about these 2 groups, that means 3rd A and 4th A. So in the second year syllabus, we are going to learn the remaining groups. So they are from 5th A to 8th A. Now in this class, we are going to discuss about the 5th A group elements. In this 5th A group elements, the first 2 elements are the non-metals. Nitrogen and phosphorus, both are non-metals. Arsenic and antimony, strontium, both are metalloids. And final element is the metal. So from this observation, so we can understood when we are going from top to bottom, That means from nitrogen to bismuth, non-metallic character decreases. In the same way, metallic character increases. And now we are going to discuss about the occurrence. Occurrence or abundance. The first element, nitrogen. Nitrogen 78% by volume present in atmosphere, and nitrogen that is present in earth crust in the form of nitrates. For example, NaNO3, it is called also chili saltpeter, and another example is the KNO3, potassium nitrate. It is called also Indian saltpeter or Bengal saltpeter. This is about the occurrence of nitrogen. Next element is phosphorus. It is present in the earth crust in the form of apatite family. The general formula of apatite family is Ca9 PO4 taken 6 dot CaX2. Here X means fluorine or chlorine or bromine, etc. And phosphorus that is also present in bones and living cells of animals, etc. And phosphoproteins, they are present in milk and eggs, etc. And final three elements, arsenic, strontium and bismuth, they are occurring in the earth crust in the form of sulfide ores. This is about the occurrence of 50A group elements. Electronic configuration. 50A group elements, nitrogen, phosphorus, arsenic, strontium and bismuth. Nitrogen electronic configuration already I am written on the board. Atomic number is 7, 1s2, 2s2, 2p3. Phosphorus 15 atomic number, 1s2, 2s2, 2p6, 3s2, 3p3. Arsenic atomic number 33, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 and 4p3. Strontium atomic number 51, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10 and 5p3. Bismuth atomic number 83, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10 and 6p3. Now observe the outer shell electronic configuration in each and every element. Nitrogen, so it has the 2s to 2p3 configuration. Phosphorus, it has the configuration of 3s to 3p3. Arsenic 4s to 4p3. Strontium 5s to 5p3. Bismuth 6s to 6p3. By the observation of this one, slightly we can say, so these elements have similar electronic configuration in the outer shell, that is S2P3 configuration, but there is a variation in the principal quantum number value. Nitrogen 2, 3, 4, 5, 6. That's why straightly we can say the general outer electronic configuration of 50A group elements is NS2NP3, and by the observation of this one, S orbitals are completely filled, P orbitals are half filled. That's why these elements have somewhat more stability as compared to the previous group elements, that means 4th A group elements. This is about the electronic configuration of 5th A group elements. Periodic properties, these are repeated properties at regular intervals in the periodic table. The first one is atomic and ionic radii. So atomic size or ionic radius. So for example, I am assuming it is one of the atom. The distance between the nucleus and the electronic cloud of outer shell is called as atomic radius. So observe the 50A. So nitrogen, phosphorus, arsenic, strontium and bismuth. When we are moving from nitrogen to bismuth, atomic numbers regularly increasing. Due to that reason, atomic and ionic radii also increases. Particularly, there is a large increase in covalent radius from nitrogen to phosphorus, and there is a small increase in covalent radius from arsenic to bismuth. This is about atomic and ionic radii. Next one is ionization enthalpy. What's the means of ionization enthalpy? This is assuming as an atom. It is a nucleus. Some electrons are revolving around the nucleus. Now I am defining the ionization enthalpy. The minimum amount of energy is required to remove one electron in the outer shell is called as ionization enthalpy. So how it changes in fifth year group elements? Generally we know that one ionization potential is inversely proportional to atomic size. So when the atomic size of an element is more, IP value is less. For example, if the atomic size is less, ionization potential is more. So already we are discussed about the atomic and ionic radii. When we are moving from nitrogen to bismuth, atomic sizes increases. Due to that reason, so the IP values of these elements from nitrogen to bismuth from top to bottom decreases, and these elements have typical configuration. S orbitals are fulfilled and p orbitals are off-filled in the outer shell. Due to that reason, these elements have somewhat more IP values compared to the fourth year group elements. Generally, we know that one IP1 is less than, IP2 is less than, IP3, etc. That is about the ionization potential or ionization enthalpy. And the last property, electronegativity. What's the means of electronegativity? So for example, I am taking one of the molecule here, HCl. There is a single bond in between hydrogen and the chlorine atom. So electronegativity, and defining the electronegativity, the tendency of an element to attract bond pair electrons towards itself is called as electronegativity. That is electronegativity. And how it varies in fifth year, observe there. So when we are moving from nitrogen to bismuth, so that means from top to bottom, atomic sizes increases. So due to that reason, electronegativity decreases from nitrogen to bismuth, and so there is no much change in the electronegativity in the heavier elements. That is about electronegativity.